Welcome to Orders of Magnitude. Have you ever stopped to wonder what these things could possibly have in common? The daily ups and downs of the stock market, the populations of every country on Earth, the lengths of the world's longest rivers, the spiral hidden inside a humble seashell, even the great swirl of an entire galaxy. At first glance, the answer seems obvious: nothing. They come from completely different worlds. One is money, one is people, one is geography, one is biology, and one is the cosmos itself. And yet, buried inside every single one of them, there is a strange, quiet pattern. The same pattern, showing up again and again and again. It is so subtle that for over a century, almost no one noticed it. And it is so dependable that today, tax inspectors and forensic accountants use it to catch criminals who fake their numbers. In this video, we are going to uncover that hidden pattern together, step by step, starting from something so simple it will almost feel like a trick. And by the end, I promise, you will never look at an ordinary list of numbers the same way again. So let us begin with that simple thing. Take any big pile of numbers from the real world, the amounts on thousands of people's electricity bills, let us say. Now, ignore almost everything about each number. Forget whether it is large or small. Look only at its very first digit, the first figure you would write down. It could be anything from 1 to 9. So here is the question. If you collected thousands upon thousands of these numbers, how often would that first digit turn out to be a 1? The natural answer, the one that almost everyone gives, goes like this. There are 9 possible digits. Each of them should get a fair turn. So a 1 ought to show up about 1 time in 9, a little over 11%. It feels obvious. It feels fair. And it is completely, provably wrong. In real data, the digit 1 does not appear 11% of the time. It appears about 30% of the time, nearly 1 in 3. While the poor digit 9 limps in at under 5%. The numbers of the world, it turns out, are playing favorites, and in this video, we are going to find out exactly why. Let us not take this on faith. Here are the populations of every country on Earth. We do nothing clever. We look at each number, take only its leading digit, and keep a running tally. Watch the bars. The ones tower over everything. The twos are next, but shorter. And the staircase falls away, step after step, down toward 9. Maybe, you think, that is something special about populations. So let us change the data completely. The lengths of the world's rivers, the areas of every lake, the molecular weights of chemical compounds, the numbers printed across a single day's financial pages, the Fibonacci sequence, the powers of 2, different worlds, different units, different centuries of measurement, and yet, the same lopsided staircase rises in front of us, again and again and again. Something is going on here that has nothing to do with rivers, or money, or rabbits. Something structural. This pattern has a name. It is called Benford's Law. Frank Benford was a physicist at General Electric who, in 1938, collected more than 20,000 numbers from anywhere he could find them. Baseball statistics, atomic weights, the addresses of people listed in a magazine, and showed that they all obeyed it. But he was not the first. Half a century earlier, the astronomer Benford Newcomb noticed something strange about the library's book of logarithms. The early pages, the ones beginning with a 1, were gray and soft and worn from use. The later pages were clean. His colleagues, it seemed, spent far more of their time looking up numbers that began with small digits. From a smudge of graphite on a page, Newcomb guessed at a law of nature. And that law is not a vague tendency. It is exact. Its exact shape hides a single, beautiful idea. And to uncover it, we have to stop thinking about digits altogether. Here is the first shift in perspective. The quantities of the real world do not live on an ordinary ruler, the kind where 1, 2, 3, 4 are spaced out at equal intervals. They live on a multiplicative 1. Think about it. The step from a village of 1,000 people to a town of 10,000 feels like the same kind of leap as the step from 10,000 to 100,000. Each is a tenfold jump. Growth in the real world does not add, it multiplies. And the natural home for things that multiply is the logarithmic number line. On this ruler, we do not place numbers by their size, but by their number of digits, by their order of magnitude. 1, 10, 100, 1,000 now sit at evenly spaced mile markers. The whole sprawling range of the world's quantities is folded into a calm, regular staircase of powers. Now look closely at the space between two of those markers, say between 1 and 10. Every number in this decade that begins with a 1, from 1 up to, but not quite reaching 2, lives in this stretch on the left. And on the logarithmic ruler, that stretch is wide. It takes up about 30% of the gap. Now find the numbers that begin with a 9, from 9 up to 10. They are crammed into this thin sliver on the far right, just 4.5% of the same gap. Stop and notice what just happened. We have not done a single calculation. We have not assumed anything about populations or rivers. The geometry of the ruler itself, the simple fact of measuring by magnitude, already favors the 1 over the 9, by almost 7 to 1. Now let us put data onto this ruler. Imagine a collection that spreads across many orders of magnitude, small towns and vast megacities, penny stocks and blue chips, grains of sand and mountains. On the logarithmic line, a collection like that scatters its points fairly evenly, decade after decade after decade. And here is the punchline of the whole idea. If the points are spread evenly in logarithmic space, then the fraction of them that fall into any band is simply the width of that band. The wide band, the one that starts with 1, catches the most points. The thin band, the one that starts with 9, catches the fewest. Let us lift those widths up and stack them as bars. And there it is. Built from nothing but the spacing of a ruler, the same lopsided staircase we measured in the real data. It was never about the digits being special. It was about the ruler. We can now make this perfectly exact. The width of the band for a digit d is the logarithm of where the band ends, minus the logarithm of where it begins. Log of d plus 1 minus log of d. And by a basic rule of logarithms, that collapses into one clean expression. The logarithm, base 10, of 1 plus 1 over d. That is the entire law on a single line. Let us test it. Put in d equals 1. We get the logarithm of 2, which is 0.301, 30%. The mysterious number we met in the very first minute was simply the logarithm of 2, wearing a disguise the whole time. Put in d equals 9, and out falls 4.5%. Every step of our staircase, predicted exactly by a formula you could write on your thumbnail. But why should real data spread itself so evenly across the scales in the first place? To really feel it, follow the money. Wealth in the real world is wildly, brutally uneven. At the very top sit a handful of giant companies worth trillions of dollars. Just below them, a few hundred large firms worth billions. Below those, hundreds of thousands of mid-sized businesses worth millions. And beneath them all, millions upon millions of tiny shops and ordinary people worth merely thousands. Look at the shape of that pyramid. The richer you are, the rarer you are. A tiny crowd at the dizzying top and a vast ocean of people at the bottom. Now line every fortune up by its size, because each step up the ladder multiplies the money, tenfold, 100-fold. The amounts smear themselves smoothly across the orders of magnitude. And we have already seen what a smooth spread does. It hands the digit 1 its 30%. Money compounds, cities compound, fortunes compound, each one growing in proportion to how large it already is. And anything that grows by multiplying carries Benford's fingerprint. It is not magic. It is the signature of wealth itself. We should be honest about where this breaks down, because a law you cannot break is a law you do not understand. Benford's law is not a law of nature like gravity. It needs data that ranges freely across many scales and is not fenced in. Take human heights, measured in centimeters. Almost every adult is between 100 and 200 centimeters, so nearly every number begins with a 1. No spread, no Benford. Take lottery numbers, or dice rolls, or a telephone area code. These are assigned by design to be uniform, and they stay stubbornly, deliberately flat. But let a quantity grow on its own, across towns and cities and nations, across cents and millions, and it is quietly pulled toward that one curve, as if the curve were a kind of gravity well in the space of all possible data. Which brings us at last to the fraud investigator. When a human being sits down to invent numbers, padding an expense report, inflating revenue, fabricating a tax return, they sprinkle their digits more or less evenly, because an even sprinkle is what randomness feels like to the human mind. But genuine financial data obeys Benford. So the auditor does not need to verify a single receipt. They simply count the leading digits across the whole ledger and compare the staircase to the one the law predicts. This is not a thought experiment. It has been used to flag manipulated corporate accounts in the collapse of Enron. It was used by economists who showed that the figures Greece reported before its debt crisis deviated from Benford more than any other nation in Europe. It has been carried into courtrooms as forensic evidence and used to probe suspicious results in elections. If the ones do not arrive about 30% of the time, an alarm, quietly, goes off. The forger's own intuition, the very same gut feeling you trusted in the first minute of this video, is the thing that gives them away. So the lesson was never really about digits at all. It is that our sense of what counts as uniform, as fair, as evenly spread, lives on the wrong ruler. The world does not keep its books by adding, it keeps them by multiplying. And once you learn to see in logarithmic space, a law that first looked like sorcery, like the numbers of the universe conspiring, becomes nothing more and nothing less than the width of a stripe. If you enjoyed this video, please like and subscribe for more such exciting videos.